Today my guest is Bryan Hunter. Bryan, how are you?
Oh, good.
What are you doing?
I'm a software developer out of
Me too.
out of Nashville. Background in .NET, but I work for a company, Firefly Logic, founded back a few years back. We kind of grew out of the Microsoft stack, and we're still in the Microsoft stack, but that's where we've been. Been down in .NET since the early betas and all this as individually, and then when we started the company, we were focused on that. And then a few years back, we decided to diversify on phone stuff, with mobile off into iOS, doing iPhone, iPad, and then now we've diversified sort of on the back. We're introducing Erlang as sort of this other technology to go into the mix, this complementary piece.
Erlang. Okay. Now, I've know of Erlang and I've heard of it, you know,
Mm-hmm.
and I've always thought of it as it's a functional language.
Yep.
Which is partially correct, but it's certainly not. It's far from complete. And I just learned this last night in that conversation we had.
Yeah. Okay. Right.
But, it's more than a language.
Yep.
What else is it?
Okay, so Erlang, what is it? There's the three parts really. And when people say Erlang, they mean these three things. There's a language, like you're saying, that's it's this functional programming language. It's a dynamic programming language, and there's this odd thing that you sometimes hear attached to it called a concurrency programming programming language. Okay. And but it's basically, that comes in when people want to point out that like Scala ripped off its actual model, or Node is borrowed.
Is there a big feud?
No, not at all. I'm sort of just kidding. But lots of, in the same way that Erlang learned from other languages, but you have this language that has been around for quite a while. So Erlang the language was built out of Ericsson back in the 80s with Joe Armstrong, Mike Williams, Robert Birding, and then others, and the life of it.
It's the phone company, Ericsson.
Right, Ericsson, the Swedish telecom giant, yeah. And so they were tasked with solving this tough problem of how do you build a software switch that handles lots and lots of calls. So you think about the concurrency problems of everyone in a country picking up their phone at the same time, or in a large company, their PBX type stuff. So as you're saying, I want to transfer calls, or I want to put someone on hold while I take the other call, or I want to forward, and so there's a lot that can happen there. So concurrency matters, being able to do lots of things at the same time, and then also distribution. You've got this concept of distribution that's really there with phone stuff. Things are distributed,
right?
And it has to be reliable. People actually expect their phones to work. Like software, people don't. People have come to the expectation that software doesn't actually work. Like it crashes.
It doesn't always.
Right. Yeah. But people in previous. You think back in the '90s, like your power goes out. You pick up your phone works, and you call to get the power turned back on, this sort of thing. And so, there's a reliability that's there. You never expect it to go down. And so there's this language that grew out of there, out of Ericsson. And the reason it grew out is they did a search for trying to have something to implement this complex phone switching stuff in to meet these requirements, and they couldn't find a language to do it in. Like they tried with C, they tried with different things, and things weren't. It's the wrong level of abstraction on each of these languages, and there was so much friction involved in actually, meeting the end goal. And so they did this thing which is insane. They wrote their own language, and so they started on this project, and it kind of grew out of Joe Armstrong saw a lot of things he liked about from Prolog, and so. There are these Prolog roots to this language, and there's these functional concepts there, and so it's a strange language. And some people think it's beautiful. I really like the language, and I like the way it feels and how it compacts. Other people feel it's kind of funky, but it's the same thing. I mean, some people don't like the way that Ruby looks, and it keeps them, even though they love the things that come out of the Ruby community, like convention over config or whatever. They like these things that come out of there. They just don't like the syntax of it. And so the other day in the keynote here, that was one of the conversations that Warren was talking about. Right, he gave props to the Erlang talk that I gave here at the session, which is really cool. In the middle of this keynote, right in the middle of the keynote. But it was cool because he was talking about how he had learned a lot as he was building his Raven DB. He learned a lot by digging into Couch and learned a lot from Erlang as he was digging into different Erlang code bases, but he never could get over the syntax. And so it's like, so I put him at some other code bases for him to look at. So maybe he'll come around and he'll love it now after demo. But so back to
probably write his own functional language.
You're exactly right. Yeah, he probably will. He'll do it in a weekend, and it'll be great. But well, he's married now, so we're not really sure if his productivity will change now.
Never know how it will inspire you.
Right. So there, outside the language. There are actually three parts to Erlang. So initially you talk about the language, and that's what you think of. There's also a runtime, the Erlang runtime system. And you could think maybe JVM or something like that, or you might think like the CLR, and that's what I thought for quite a while. And I know after a certain amount of time I realized this isn't like that. This is actually an operating system. The Erlang runtime system does things that operating systems do.
Such as?
So in .NET or in Java or wherever we're at, I mean, one of the things is just to preface, one of the things when I talk about this stuff, I always am comparing things against .NET because that's my background and so on. But it sounds like when I'm talking about these things that are really great about Erlang, it sounds like I'm bashing, but it ends up being like these things are different. So and the thing I'm most familiar with is .NET. So just to go from there.
I remember you made this point last night. You said that Erlang is good at some things,
right?
As at other things, and I'm certainly guilty of this. I want to force .NET to do things that maybe it's not the best tool for doing. That's just a tool that I know. I'm comfortable with it.
Exactly.
As opposed to looking around and saying, is there another tool like Erlang that might do that better?
I think to that point, I've sort of had this. After I got caught on fire, we can talk about how I got introduced to this, and I saw some remarkable things that sort of led me on this path. But I'd like people sort of this mission. I'd like people to look at Erlang in the same way they look at like JavaScript or T-SQL.
Right.
Because it's another tool in their bag, and it solves some things you solve a lot better when you go off into T-SQL and do it than trying to do it inside of C#.
Absolutely.
But people don't feel freaked out about that. They don't feel freaked out about using JavaScript. But you introduce this other language, and sometimes people get a little freaky about it, and it's people have this sort of sense that maybe this thing is encroaching. But the interesting thing, like you're saying, is they're so radically different. The things that Erlang is exceptional at, .NET pretty much sucks at, and vice versa. Okay. There's a whole set of things that .NET great about, and those are not the things you want to use to write. You don't.
Okay, let's focus on things that Erlang does well, particularly the things that .NET falls short of.
Well, to do that, let's talk about that operating system bit.
Okay, that's right.
So the Erlang
start
runtime.
Calling it a runtime, and
right.
It's more than a runtime.
Yeah. So sort of these sweet spots in the language are a lot of those are supported by this Erlang runtime system, and the sweet spots for Erlang that people talk about over and over are around concurrency and distribution and reliability.
Okay.
And there are these other things. It's open. It's this open source language, and people like that and appreciate that. And it's cross-platform. Works just as well on Windows, Linux, and Mac, and so on. And so that's another nice thing. And it has this sort of proven track record. And we maybe touch into that and how I kind of got into it. But so
concurrency.
Concurrency. There's this. Think about like when you approach how you're going to do many things at the same time, and this happens more and more now. There's the sort of tired saw about functional programming is it's like, well, it's going to be the wave of the future because machines aren't getting faster, they're getting wider. We get more cores and all this, and that's the over and over thing that you hear when there's a selling point for functional programming. And it's but there's something to that, but so that is a real issue. And as you deal with concurrency on threading is what you just like, okay, I'm going to fire up threads. And so what do you think of when you hear like mutex, semaphore? What does it give you this warm, cozy feeling?
No. So threading or multi-thread programming is dangerous. It's inherently, at least .NET it is.
It's very dangerous.
Concurrency causes a lot of issues. Raise conditions,
deadlocks,
any kind of conflict for resources.
Yeah. And you have this issue of mutable state. You've got, you can blow things up, and you have all sorts of crashes. So the thing that I sort of just came up with in the meeting yesterday, and people in the session yesterday, and people hee-hawed at it. They thought it was funny, and I got some tweets off of it. But it's like there's this inverse relationship between a developer's seniority and their eagerness to take on threading.
Oh, people that fresh out of college.
The kids, it's like I want to do some of that. I'll be
like the thread.
Yeah, it's like, oh yeah.
And you don't know what you're getting into.
So there's like all this in there, bullets flying everywhere, toes flying off, and all this in the code.
And some of the stuff you realize, that's kind of dangerous.
Right.
You're trying everything else before I stop.
Right, exactly. And so it's sort of a tug, because we're at this spot where you've got this big box that scales wide. But you're not taking advantage of it because you've seen like the bodies, So you've seen this thing behind you, this trail of like carnage behind you, and so it's a dangerous model. And Microsoft with the parallel libraries and the stuff going in C#5 coming along, this is something they continue to address, but. Where are we really with even the parallel libraries? You talk with Stephen too, brilliant guy.
He's been on the show.
Oh, cool, yeah, brilliant guy. And you talk to him about with Erlang, and he's like, yeah, and so he, this guy knows all about Erlang. He knows about the problems that they're facing, but what they're doing is they're not doing what Erlang does now. They're making what is there better, and they're making it a little safer, that sort of thing, and they're making things like easier to do this really hard thing, but there's still danger involved. And he'll be the first to tell you that there's still danger involved here. It's like this doesn't solve it for you. And the way that it's solved so radically different in Erlang is you don't have threads in Erlang, and you don't code you code everything sequentially. And so what you do is you write these, you code process, you run processes. And so in any other language you think of process, it's this big heavy thing. And so there's a significant cost of firing up a process. Well, process is a different concept entirely in Erlang. It's a thing inside of the runtime and it's very light. It's very light even compared to a Windows thread or to a Linux thread. So the weight of firing up a thread is about a K. So a kilobyte, and the weight of building a thread in say .NET is like a megabyte or 2 megabytes. So like 1,000, 1 million. So a significant difference there. And even the way that the scheduling happens between how efficient it is to do context switches between threads and switches in Erlang between processes is very light. And so it's an interesting model there. But so these
are the operating system parts of Erlang that you're talking about.
Yes, and so this is
context switching. That's an operating system.
Yeah, and here's one of the things. If you're writing an operating system and you have to be able to support like word processors and video games and all these generic things, you have to think about a lot of stuff.
Right.
But if you're writing an operating system that's only goal in the world is to make sure that Erlang code can run, you can have great concurrency.
You can optimize for
you can optimize for that. And so it's built to support the language.
Okay.
Interesting thing, so you can have not just like on Windows, say if you fire up Outlook, you eat up like how many threads, 100 threads or something, a lot of threads, and so your box feels it.
Right.
And if you're writing code and you're running like several hundred threads in something, it's like, and you get to like some number of threads and your box dies, And so with Erlang, the idea of a process. So if you have these things that can run concurrently, you can fire up. One of the demos I have, and that's sort of in the community, is that you fire up a process in Erlang that's whole job is he comes up and he creates another child process, and they send messages back and forth to say, hey, how's it going? I'm good. And then this guy dies, and then you have this sort of cascading series. And so you can create, say, 1 million processes in like a second and a half on my laptop.
Okay.
And so that tells you the sort of different level that we're talking about. It's not even the same game. This is it's a different concept entirely. It's not.
Okay.
And so these processes are out there, and they're all independent. you imagine like the code inside of the process running as a lonely guy sitting in a room, and another lonely guy sitting in a room over in another process, and the only way that they communicate is through message passing. And so this guy's hungry. He doesn't like go over there and grab the guy's ham sandwich out of the other thing and take it, and the other guy's lifting his hands up. They send messages back and forth, and so it's like, send me the ham sandwich, or that sort of thing. And so you end up not having this danger of shared state between them. There's no shared state between the processes. This
might be one of the best metaphors. So shared state is a ham sandwich.
A ham sandwich. So there's a lot of safety you get out of pure message passing, and this is where Scala really does great things, because they borrow from this, and they take this example of the success and they use this.
Did Scala borrow from Erlang, or Erlang borrowed from Scala?
Oh no! I mean, there's sort of absolutely Scala borrows from Erlang here, but there is sort of there's a April Fools that Joe Armstrong and Robert Birding they do, where they're talking about, we really owe a lot to Scala, and it's like it's their reverse thing on it, and so concurrency, like I was saying, you have these many things running side by side, and the switching between them is handled really efficiently. And interestingly, it's like as you create more and more cores, you have more and more cores in a box, things scale linearly. Like when I write my WPF app and I'm running my desktop stuff, I basically have two things going on: my background worker thread, and so I've got that. Okay. And if I feel real adventurous, I might create a thread, and I'll be able to take advantage of, say, another core out there to do something. But it's really, things aren't going to keep on going. So if I had 64 cores on something, I'm going to be still just eating this 1 to 3 over here, Okay. So I'm not going to be taking very much use of the box and be locked down on there, because everything is stuck there. But with Erlang, you're writing these small bits, these bits that are in processes, and things scale linearly, I think up to right now, like 40 cores or something like this. If you have the code that's written in an idiomatic way, you're writing it. You could still write a single. You could write Erlang code that is not using concurrency, and there are really good reasons to do that as well. But if you need that, you can scale across hardware, and as hardware gets bigger, they'll solve things so that it scales linearly to 64 and to 128 cores and so on. And so this is something
done by kind of bundling up our instructions in these processes. Is that the idea? That's
right.
How it handles concurrency?
Right. So processes are super cheap to create. So anytime that you need something to run side by side, you just fire up a process, and it's this thing that can be off on its own core. It's not tied to anything, so it can run truly in parallel.
And is it a virtual machine that takes care of where that actually runs?
Yes. Okay. So you don't think about any of these things that are low level about what the hardware looks like. You create processes. So interesting thing is, we get to distribution, and so you end up even with this idea of saying, okay, well, I can have lots of processes here on this node. So a node is an instance of the Erlang runtime. It's an instance of the VM. Okay. So you have a node running, and you got all these processes doing things. You can also say, you can talk to another node on the same box or on another server. And the code that you're writing is the same code that you write. So you don't change things just because there's location transparency. You don't care it's on another machine other than maybe network cost. But as far as the code goes, you don't have to care about the difference.
Okay, so I have, let's say, this is something I do in .NET, distributed architecture, and maybe I'll have a component running here on machine A, and a different component running on machine B, and I expose some interfaces so they can communicate with one another. And I do that for a lot of reasons. Load balance. Just because this is busy, I don't want this to go down, or maybe I always want to distribute it. But I have to know that machine's over here. I have to know when to call it. I have to tell it, okay, it's hitting this web service over here. I'm remoting over this machine or something like that. Yeah. The same thing must be true.
You have a very simple, so again, the distribution is built in at the core there are these distribution primitives that are in Erlang, so that you have, say you pull up cat, and you have a node called cat, and you have a node called dog. And so you've got these two nodes. You can do as simple as from the Erlang shell. So this is like the REPL, that you're in, the read eval print loop. So you can say net ADM ping, so you're up here in dog, or down here in dog, you can say net ADM ping cat. And at that point, cat and dog know about each other. And so you can say, okay, who all do you know about by typing nodes? And you'll get this list that says cat knows about dog and dog knows about cat.
Okay.
And you introduce a third node in here, and so cat knows about bird. You know, after you do an ADM, and then there's this gossip protocol.
The language supports opening communication between these nodes, which you have to do explicitly.
So right, you say, hey, I want to link these together through net ADM ping, and so then the fact that dog knows about bird, cat knows about him too, all of a sudden, and so there's this gossip protocol that goes between them, and they all know about each other. And the same thing is you create it on another machine, and you know about, so this machine over here knows about one node over here through net ADM ping. All four of the boxes are now part of this sort of mesh, is a way of looking at it.
Okay.
And so, and once they're in here, you can do interesting things like say, I want to run this code on all of the nodes. And so they're sort of patterns. Like there's a concept in distributed computing that's really taken seriously in Erlang. It's called no masters. So you don't have some boss in the middle doing work. And you could, I mean, of course, you could have some boss in the loop, but the idea is you want to have a series of peers. Okay. So everyone has the same capabilities, and so you get to the spot then where it is you need more capacity wide, or you want more redundancy. You know, so you know there's the different reasons of having distribution. You know, sure. There's this terrible cost you pay for distribution and complexity, and the tools that we grew up in, and the tools that everyone grew up in, unless you happen to grow up in Sweden and you went to Ericsson. But so there's terrible costs there, but we still feel compelled to do it. And so here, that complexity, that friction is really removed, where these things are handled at the base and they're done for you. Same thing with concurrency, those things are handled at the base and sort of done for you. And so you think about what it gives you when you have this ability to do lots and lots of things in parallel safely, and you also have the ability to distribute code across multiple nodes, and it's simple. You've created this reliability story that starts coming in, but on top of that, there are these primitives built in for reliability. And so that was sort of that third leg that we were talking about earlier on what they were designing this thing to do. And so reliability comes in. So if you spawn a process.
So third legs was the language, the virtual machine / operating system, and
and then there's the OTP, which is the Open Telecom Platform. This is a funny old name, but it's the series of libraries like the things to do I/O, the things to do OS, and also a set of design patterns that are in there. And some of those design patterns, like they're like behaviors, like gen server. It's like this cooked way of writing a thing that sits there as a server and takes requests, and it behaves very well. And so there are these things that are cooked in and certain ways of doing things in Erlang, and that's sort of bundled into this thing called OTP. But on reliability, you would use, say, GenSup, or which is this supervisor. And so lower level than the supervisor, what the GenSup is built up on is this idea that when you have a process here and you spawn another process, well, you can have a link between the processes there. You say, this process knows about this process, and he can know when this process dies. Okay. And so if you have, and it doesn't matter if this process is on this box and this is on this other box, he can spawn a process on another box. And so and he can know about when this guy dies. And so it's interesting, you can have these guys being like canaries in a way, and to let you know that something's wrong over here. But right. And so, but this model, you have built up on top of this primitive of links and monitors between processes, you have these supervisors. So the supervisor is a way of saying, I have a strategy. When this, if I'm going to fire up this, when this guy dies, I need to know about it, and I'm going to have a retry strategy. I'm going to say, okay, in 2 seconds, I'm going to try to recreate it and bring him back. And if it fails again, I'll do that up to 6 times or whatever. And so you define your strategy here, you know. And then what happens after you meet that? Do I die? Okay, and then my supervisor catches this and handles what he's going to do about this supervisor. So you have supervisor trees. So you can look at this top, up, down. You have supervisors that can have supervisors that are below him. Supervisors in the leaves are then these workers.
Okay, so this concept of everything with supervisors are monitoring, and there's some call it advanced, some notification
Right.
when something dies, and then
The
various
strategy
standard ways of handling that, like retrying a certain number of times before giving up. And
yeah, so you've written your good code, right?
That code, that stuff's already built in.
Yes.
Yeah, we don't have to write that code in order to just.
No, you just use the stuff that's there, and so well, exactly, and so you use what's there. So you think about apps that are up, and they're out there going. There might be different reasons the thing is failing, and so you have this option of what your strategy is going to be. About, do I restart him, or do I just say, this work here, I know that something's just bad about this. This is like a poison thing, and this is poison work, and I'm gonna log this somewhere that some human can go and do something with it or whatever. But generally, what you're doing is you're writing good code. You're writing bug-free code, right? And you're writing tested code, and you're writing all this out there. But still, the world has ways of introducing problems, and so network cables get cut. Someone, the bulldozer comes and cuts through the fiber, or someone yanks a hard drive out, or what failures. So, or on a problem that we deal with on web servers is you build up lots and lots of heat on a box, and then the garbage collector kicks in, and that takes things off over the edge, and you start queuing, and the whole system fails. Mm-hmm. You have so things outside of your control can happen, or like this. It's like, that's not my code. That's the garbage collector coming in. So I got hit by something, and so in those cases, that's what the supervisor stuff is really to help you. Things that are sort of outside of your control is a really good. So there's this concept. Instead of having a bunch of try catching all through your code, you say let it crash. And so funny, this let it crash strategy is how you end up with systems in Erlang that have incredible uptime. I've ran into the wild. Like my first introduction to Erlang, I was at a client where we were looking at a huge code base, 20 million lines of C++, and there's a bunch of C# stuff that was sort of sitting in, mixing in the mix, and these 12 teams that were working on this code. And we were helping, just had a sort of eval of all of the problems here. So we were providing a second set of eyes on this code that they had there. And event storms here, and class hierarchies of 12 levels deep here, and problem. Get this one spot, no problems. And we were like, what's going on here? And of course, it's going to be this Erlang system. I never heard of Erlang at the time. But the system in the middle of all this chaos and pain. And this one system had been up for 5 years, and they hadn't had any trouble with it. So there's like 5 years of uptime.
Okay.
And have you ever even heard of anything like that? and so there are these switches at Ericsson that have 9 nines of reliability. Wow. And so you think about that 9 nines. It's crazy. You're talking about 32 milliseconds a year is what your service level agreement would be to say that. And so not that you need 9 nines. you might be just fine enough with 2 nines. It depends on the problem. So it's one of the things about all this is like there's a book called "Learn You Some Erlang for Great Good," and there's a recurring bit, and it's an online free book. You can search for it and find it and read it and learn all about this stuff. But there's a recurring section there called "Don't Drink Too Much Kool-Aid," and he's like Erlang can do these great things, you make sure that you're not doing it just because it can, kind of thing. And
sure.
And so it's easy to get really excited about this. And one of the things I always like to say is, it's like, figure out where it fits. This isn't the thing to replace all of your code in. This is a thing that as you approach this, you need to take a really cautious approach. If you like what you see, and you like to say on the reliability story, like you like the fact that Facebook is using Erlang for their chat system. It's the back end for that. You like the fact that you're writing something that's good enough for GitHub to use for their back end, and you're using for Amazon to write simple DB in, and CouchDB written in Erlang, and RabbitMQ, and T-Mobile's chat, or T-Mobile's messaging system back to Erlang. And so pretty much anytime you pick up a phone as well, you're going through some Erlang somewhere. So, so if you want to hit that sort of thing, you need to figure out, you don't want to take on a system that size as your first project. And so you have to figure out, like, you're in love with this thing and you feel like it might fit. Don't throw out your .NET. What you need to do is you need to figure out a way of creating proofs of things that you might think where you hit a sweet spot, And you might also look at what your interop strategy is actually going to be. And so one good interop strategy is to introduce RabbitMQ. So your first way of
MQ
yeah,
is
so it's a queue. So it's a message queue. So or you could use MSMQ. I mean, but have a queue in the middle. But Rabbit I like. And so a way of introducing Erlang is to introduce RabbitMQ, which is written in Erlang. But it's very good queue.
so you drop messages on it and they get
Right, so you publish and subscribe, and you can have competing consumer, and you can distribute this across multiple boxes, and
it's
so
all done asynchronously.
right, and so that would be a great way to introduce Erlang, because you can have your queue there, and you can publish, and whoever's going to subscribe and actually do the work, that can be .NET code, and you can have a proof going along saying, like, I'm going to write the same thing. This seems like a real sweet spot for Erlang, and I'll see if I can flip this in and see if it works. So you can, and you can have, so the point of interop is maybe Rabbit to begin with, and so you don't have to eat the whole thing.
Sure, yeah, so it's more disconnected. Using queuing is a lot more disconnected.
Right, and so you've improved your C# code already. So I mean, in this process of you've made your C# code base better, and you've also given yourself a chance of tying in things that are maybe more appropriate to the task. Like instead of trying to rewrite Erlang inside of .NET.
right. So let's wrap this up. I think your big point here is really well taken, which is that there are things that Erlang does really well, does better than .NET or Java or some other general purpose platform, and those are the areas that you really want to start looking at. Maybe this little piece of it I should be moving to there. And then there was a concurrency, there is high uptime, there is distributed computing.
Yes.
And is that it? Those are the big three?
There's a thing where your code also can shrink incredibly, and we didn't touch on this through pattern matching, and this is from these prologue roots, and I'll just a real quick second about that. The way of thinking about pattern matching and how it can shrink your code, pattern matching is like the change machine. You have quarters, dimes, and nickels, and things can fall through, and pattern matching works like that. So you have this declarative way of saying how you're going to handle things instead of having bunches of ifs and switches. And so I've seen code that I've actually written to replace C# code, code bases that were 30,000 lines of code boiled down to 1,000 lines of Erlang.
Oh, okay. So it's much more terse now.
Yeah, and more readable, actually, in that sense. And a funny, odd thing, usually concise doesn't mean more readable, but in some of these cases it's declarative. You look at it, it's like, I know what that means.
Okay. All right, and so if I'm just getting started, then, like, let's imagine for a second that I've never worked with Erlang before.
Right on.
Where would the first place I go?
Okay. The first place you could go is to erlang.org, but you're gonna see the downloads to pull down the stuff. But probably I have a post on my site that has a set of links, and it's it's targeted at this .NET developer coming into this, and so it's to help .NET developers that maybe haven't spent a lot of time over in Linux. Well, you don't have to spend time over in Linux. You can do all this stuff in Windows, and it's like to take you in that background and get started from top to bottom with all the links. And so that's out on codeswamp.com.
Codeswamp.com is your blog.
Yeah, right. Yeah.
Brian, thank you so much.
Thank you so much. I really appreciate the chance to talk to you about Erlang.
I appreciate it. I learned a lot from last there too.
Yeah, all my buddies, any chance at a bar, they've heard this talk a dozen times, and so we get to do it in a conference room, and maybe at a bar later. Okay, cheers. So I just say technology and friends?
For example.
Okay, technology and friends.